Hello, everyone. I'm Chaitra Satyaprakash, and I'm really excited to share some of our year two updates of our three-year project today. So we're working on a brain organoid project to try to understand the brain-related disorders that we see sometimes in DMD. So we know that there's a wide spectrum of different neurological disorders that we see in DMD, including autism spectrum disorder, epilepsy, language and learning disabilities, and intellectual disabilities. And the goal of our project is to understand more about the function of dystrophin in the brain, especially the different types of dystrophin, the long and the short isoforms, and how loss of dystrophin in DMD boys could cause some of these disorders. So we've been using urine-derived cells in our lab donated by boys with DMD at our National Center Hospital to make induced pluripotent stem cells. And these were used to make brain organoids in the lab, which have a lot of the characteristics that we see during brain development. So this is a really powerful tool for us to try to understand the specific cellular and molecular processes that are happening during this time. The aim of year two was to try to understand a bit more about how dystrophin affects neural differentiation, what its role is, as well as potentially looking at glial activity, synapse formation in the brain organoids. But it turned out that for us, neural differentiation was really the most interesting aspect. So we found that DP140, which is a shorter version of dystrophin, is highly expressed in the brain organoids during early differentiation. In fact, we see that the larger dystrophin that you see in muscle, as well as a much shorter type of dystrophin, is expressed much later. And using our model, we're able to see the cell types that these DP140 proteins are expressed in are called the neuroepithelial progenitor cells. And these are important for making neurons. So we hypothesized that there's some kind of deficit that occurs when DP140 is lost in DMD brain organoids. And that's what we've been really trying to understand this last year. And to do this, we've been doing lots of quantification, lots of measurements in the brain organoids, looking at the different neuron cell types, trying to understand how the mutations which lead to autism spectrum disorder in DMD boys could affect neuronal production during development. And we're doing lots of exciting analysis to try to understand a bit more of this. I won't go into the details, but that also leads into the next step of our project, where in our final year of this grant, we'll be doing single-cell RNA sequencing to get a snapshot of the gene expression changes that occur due to these DMD mutations. So I'll wrap up my presentation there, but do feel free to get in touch if anybody wants some additional information. Thank you.
Thank you, Chaitra. I'm Yoshitsugu Aoki, Director of the Department of Molecular Therapy and a consultant neurologist. Building on Chaitra's presentation, I'd like to highlight two brief points. First, this research originates from basic science in Japan, but has been made possible through close collaboration with Defeat Duchenne Canada, reflecting a shared commitment to families worldwide. Second, cognitive and behavioral challenges in Duchenne are often less visible than muscle weakness, yet they are a common concern across countries. This is not yet a treatment, but it's an essential step toward improving quality of life for the mind as well as the body. We thank the Canadian and global Duchenne countries for their continued support.